Before we talk about galaxies, before we talk about redshifts, dark energy, or the Big Bang, we have to talk about a mistake. Not a scientific mistake, not something you can fix with better math. A human mistake. A mistake that lives inside the way your brain has been trained to understand reality since you were a child. Because the question, if the universe is expanding, what is it expanding into, feels like the most natural question in the world. It feels obvious. It feels unavoidable. To see why, we have to travel back to a time when the universe wasn't a scientific problem. It was a boundary problem. A time when the world still had edges. Imagine a wooden table, a candle burning, a quill, a man leaning over a map. Not a modern map with satellite precision, but a map drawn from rumours, voyages, and fear. The coastline is jagged and exaggerated, rivers are too thick, mountains are drawn like teeth. And out beyond the last known shore, the paper becomes empty. Not because the cartographer ran out of ink, but because the world in the human imagination ran out of certainty. And in that empty space you often find something written in Latin or in some other language of authority. Here be dragons. Not as a joke, as a warning. Because for most of history, the edge of the known world was not just geography, it was psychology. It was the place where reality became untrustworthy. People imagined walls, domes, infinite oceans, a ceiling above the earth. They believed that if you sailed too far, maybe the water ended, maybe it spilled into a void, maybe the sun stopped rising, maybe the sky itself cracked open. And if you're modern, you might smile at that. You might think, how could anyone believe the world had an edge? But it wasn't stupidity. It was the human mind doing what it always does. It was taking the only world it had ever experienced, a world made of surfaces and containers, and stretching that intuition as far as it could go. Because everything in our lives has an outside. A house has walls, a room has a ceiling, a lake has a shore, a city has borders, even your own body has skin. And beyond that boundary, there is always more space. So when ancient people looked at the sea, the question wasn't philosophical, it was physical. What happens if you go too far? What is beyond the boundary? What is outside the world? Now, fast forward. The maps are gone, the dragons are gone, the oceans have been crossed, the earth is no longer a mystery, and yet, here we are again, standing at another edge. Only this time, it isn't the edge of a coastline. It's the edge of the universe. Because when you hear that the universe is expanding, you instinctively picture the same thing ancient people pictured with the sea. You imagine a thing spreading outward into a larger emptiness, like smoke filling a room, like ink spreading in water, like a balloon inflating inside a house. And that picture is so strong that even if you've never studied astronomy, your brain snaps to it instantly, because your brain is a machine designed for survival, not cosmology. It doesn't think in curved space-time. It thinks in containers. It thinks in rooms. It thinks in inside and outside. So when the universe expands, your brain asks, into what? And what you're really asking is, what is outside the universe? Which is just the modern version of the ancient question, what is beyond the sea? Most people picture the universe like this. There is a giant empty space, like a black room, and inside that room there is the universe. The universe is filled with galaxies and stars, and as time passes, it expands outward into the room. It feels reasonable, it feels clean, and it's wrong. Not because the universe isn't expanding, but because the room you're imagining doesn't exist. The universe isn't a thing inside space. The universe includes space. That is the first big correction, and it's the correction that changes the entire question. Because if the universe includes space, then asking what it's expanding into becomes like asking what is north of the North Pole. The grammar works, the words make sense, but the concept collapses the moment you try to picture it. Imagine you are a character inside a simple video game world. Not a modern open-world game with infinite terrain, but an old classic world where you can walk in a straight line forever because the edges loop. Walk off the right side and you reappear on the left. Walk off the top and you reappear at the bottom. To the character inside the game, there is no boundary, no edge, no outside. There is only the world. And from our perspective, outside the game, we can see the screen, the hardware, the room it sits in. So you might think, aha, that's the outside of the game. But here's the key, that outside only exists for us, not for the character, not for anything inside the world. Inside the world, the concept of outside isn't just unknown, it's meaningless. Because outside is not a location inside the system, it's a different kind of description. This is the hardest idea to accept because it feels like we're changing the rules mid-sentence. We grow up thinking space is nothing, just emptiness, just the background, a passive stage where matter performs. But modern physics tells us something far more unsettling. Space is not nothing. Space has structure. Space can stretch. Space can bend. Space can ripple. Space can carry time along with it. And once you accept that, the universe stops looking like an object. It starts looking like a relationship. Not stuff inside a box, but the box itself becoming bigger. And that is a totally different kind of expansion. Go back to those ancient maps one more time. Imagine you are an explorer, standing on the shore, staring at the ocean. Your map ends at the coastline, and beyond it, the page is blank. You might think the blank page is the edge of reality, but it isn't. It's the edge of your knowledge. The world doesn't end because your map ends. Your certainty ends. Now imagine something even stranger. Imagine the map itself is stretching. The paper grows. The distance between the ink marks increases. The cities move apart on the page, even though the cities themselves don't move. That is closer to what cosmic expansion is. Not a ship sailing outward into emptiness, but the scale of the map changing. The distances in the map increasing, the geometry itself stretching. At this point, most people bring up the balloon, and they're not wrong. The balloon analogy is one of the best teaching tools ever invented for this concept. If you draw dots on the surface of a balloon and inflate it, the dots move away from each other. Every dot sees every other dot receding. There's no center on the surface and no edge. It's a beautiful way to picture expansion. But the balloon analogy has a hidden poison in it, because the balloon expands into the air around it. The balloon exists in a room. And the human mind can't resist importing that detail into the universe. People imagine the universe is the balloon and the outside is the room. But the room is not part of the analogy. The room is the trap. The balloon is only meant to describe the internal geometry, not an external container. The real mistake is thinking in 3D objects. When you imagine the universe expanding, you imagine a 3D thing, a sphere, a cloud, a bubble. Something you could hold, something with an outside surface. But the universe is not a 3D object inside something bigger. The universe is the totality of space itself. It isn't in anything. It isn't surrounded by anything. It doesn't sit in a larger emptiness. It defines what emptiness even is. And that is why the question becomes so maddening. We don't have an everyday category for this. There is no childhood memory that matches it. There is no human experience of a thing that is not inside something. This is why people keep asking the question, not because they're ignorant, not because they're dumb, but because the question is a symptom of something deeper. Human intuition was built for forests and oceans, not for the geometry of reality. We are creatures that evolved to track prey, predict weather, and avoid cliffs, not to imagine four-dimensional space-time expanding without an external background. So when you ask, into what? You're not asking a scientific question. You're asking your brain to do something it was never designed to do. Picture a universe without an outside. If you only remember one sentence from this chapter, it should be this: the universe is not expanding into space. The universe is expanding as space. That's the pivot. That's the moment the story changes. Because from here on, we stop talking about the universe like a thing moving through a room, and we start talking about space itself like something active, something that can grow, bend, and accelerate. But now we've created a new problem, a deeper one. Because if space isn't a container, and if space itself can stretch, then we have to ask something even stranger. What is space? Not poetically, not spiritually, physically. What is it made of? What does it mean for nothing to have properties? And how did we even discover that it was expanding in the first place? Because the truth is, the expansion of the universe wasn't discovered through philosophy. It was discovered through light, through a telescope, through a cold night in an observatory, when someone realized the galaxies weren't sitting still, they were running away. In the early 1920s, the universe still felt small, not small in distance. People already knew the stars were far, but small in meaning. The Milky Way was believed to be the whole thing, a single island of stars floating in darkness. Outside it, maybe there was emptiness. Maybe there was nothing at all. And the fuzzy spiral shapes seen through telescopes, the so-called nebulae, were still argued over like ghosts. Some astronomers believed they were clouds of gas inside our galaxy. Others believed they were something far bigger, entire galaxies, unimaginably distant. This wasn't a small disagreement, it was a fight over the size of reality, and it played out in the most dramatic way possible, not in a lab, not in a classroom, but on cold mountaintops where the air was thin and the sky was sharp enough to feel like glass. Picture it, a mountain observatory at night. The world below is asleep. The horizon is black. The stars overhead are so bright, they don't look gentle. They look intense, like they're watching. The dome of the telescope creaks as it turns. The metal is cold enough to sting. And inside that dome, surrounded by machinery and quiet, a handful of people are doing something that feels almost impossible. They are trying to measure the universe. Not with philosophy, not with poetry, with numbers. One of those people was Edwin Hubble. Hubble is often remembered as a calm, confident scientist, the man who proved the universe was expanding. But in the moment, it didn't feel like a clean discovery. It felt like trying to pull a truth out of darkness using fragile evidence. It felt like standing on the shore of an unknown ocean and trying to calculate how wide it is by watching the way waves move. At the time, the technology was primitive by modern standards. There were no CCD sensors, no digital cameras, no instant images. There were glass photographic plates, long exposures, hours of waiting, and the constant risk that the cold, the vibration, or the slightest misalignment would ruin the entire night's work. But Hubble had something powerful: access to the biggest telescope on Earth. The Hooker telescope at Mount Wilson Observatory outside Los Angeles was a 100-inch giant. a machine so large and precise that it could see deeper into the sky than any human instrument before it. For the first time, the universe was not just something we looked at, it was something we could begin to measure. And Hubble wasn't just staring at stars, he was staring at those faint spiral smudges, the nebulae. He wanted to know what they were, and more importantly, he wanted to know how far away they were, because distance is everything in cosmology. Without distance, the universe is just a painting. Beautiful, but flat. With distance, it becomes a structure, a place with depth, a place with scale. So Hubble did something that sounds almost simple but was revolutionary. He found stars inside those smudges, a certain kind of star called a Cepheid variable. Stars that pulse in brightness, like a cosmic heartbeat. And by measuring the rhythm of that pulse, you can estimate how bright the star truly is. Compare that true brightness to how faint it appears from Earth, and you get a distance. It's one of the most elegant tricks in science, using the universe's own objects as measuring sticks. And when Hubble calculated those distances, the result was staggering. Those spiral nebulae were not clouds inside the Milky Way. They were far beyond it. They were entire galaxies, island universes, separated from us by distances so large that the mind almost refuses to hold them. In one stroke, the universe expanded. Not physically, not yet, but in human understanding. Reality had just gotten bigger. And the bigger reality gets, the more it starts to behave in ways you don't expect. Because once you accept that galaxies are separate islands scattered across enormous space, you can ask a new question. Are they sitting still, or are they moving? At first, that might sound like a minor detail, but it was about to become the most important detail in the history of cosmology. To answer it, scientists looked at light, not just the brightness of galaxies, but the color. Because light carries fingerprints. If you pass light through a prism, it splits into a spectrum, a rainbow. But that rainbow isn't smooth. It contains dark lines and bright lines. Patterns caused by the atoms inside the object emitting or absorbing specific wavelengths. Hydrogen has a pattern, oxygen has a pattern, calcium has a pattern, and once you learn those patterns, you can read them like barcodes across the universe. You can look at a galaxy's light and know what it's made of, but you can also do something else. You can see if that light has been stretched. Because if an object is moving away from you, the light waves it emits get pulled longer as they travel. The crests spread out, the wavelength increases. And when wavelength increases, the light shifts toward the red end of the spectrum. That effect is called redshift. And it is one of the most haunting ideas in science, because it means the universe can take something as pure as starlight and quietly distort it across billions of years. The simplest way to picture redshift is with sound. If you've ever heard an ambulance pass you on the road, you already know the feeling. As it approaches, the siren sounds higher. As it moves away, the siren drops lower. The sound waves get compressed when it's coming towards you and stretched when it's moving away. That's the Doppler effect. And light can do something similar. If a star is moving towards you, its light shifts slightly bluer. If it's moving away, it shifts redder. So at first, scientists treated redshift like a cosmic Doppler effect, a way to measure how fast a galaxy is moving away. But what they found was not what anyone expected. Because when Hubble and others measured redshifts in distant galaxies, they didn't see a random mix of motion. They didn't see some galaxies coming toward us, some moving away like a chaotic swarm. They saw a pattern. Almost all of them were redshifted. Almost all of them were moving away. and the farther away a galaxy was, the faster it seemed to be receding. This was not a small observation. This was a cosmic law. It was as if the universe itself had a built-in rule. Distance creates speed. The more distant a galaxy is, the more the universe seems to push it away. Hubble plotted it. Distance on one axis, velocity on the other. And the points lined up into a trend so clean, it felt like the universe was speaking in a straight line. This became known as Hubble's law. And in that moment, the idea of a static universe died. Because if galaxies are rushing away from each other, it means the universe is not frozen in time. It is changing. It is growing. It is expanding. Now you might imagine this as an explosion. Galaxies flying outward from a central point, like shrapnel from a bomb. And that was exactly the first instinct many people had. It's the most human interpretation. If things are moving away, something must have exploded. But Hubble's data had a strange feature. There was no obvious center. No matter where you looked, the universe looked the same. Every direction showed galaxies receding. Every region of space seemed to be stretching. It was as if the expansion wasn't happening from a point inside the universe, but to the universe itself. And this is where the story becomes truly strange. Because redshift, in the deepest sense, is not just motion, it's stretching. Light stretched into longer wavelengths, distances stretched into larger separations. And eventually scientists realized the uncomfortable truth. The redshift of galaxies might not be telling us that galaxies are simply moving through space. It might be telling us that space itself is expanding, that the fabric between galaxies is growing, that the universe is not a thing in motion, it is a thing whose geometry is changing. And once that idea appeared, it spread fast. It was too elegant, too explanatory, too terrifying to ignore. Suddenly, the universe wasn't eternal and still. It had a history, a beginning. And if you rewind expansion backward, everything collapses toward a hotter, denser past. Toward a moment when distances were smaller, galaxies were closer, and the universe itself was compressed into something unrecognizable. This was the first step toward the Big Bang, but it also created a new problem. Because the moment humans hear expansion, they reach for the same mental picture. A balloon, a sphere, a bubble swelling into a room. And that picture is so vivid, so intuitive, that it became the dominant way people imagined the universe for decades, even though it carried a hidden misunderstanding. A misunderstanding that would haunt the question we started with. Because the balloon analogy helped people understand expansion. But it also convinced them the universe must be expanding into something, and that is where the biggest confusion was born. The balloon. The balloon analogy is one of the most famous ideas in all of cosmology, and for good reason. It takes something that feels impossible to picture, a universe expanding everywhere at once, and turns it into something you can hold in your hands. You imagine a balloon. You imagine drawing tiny dots on its surface with a marker. Each dot represents a galaxy. Then you start inflating the balloon. As the rubber stretches, the dots drift farther apart. And what's beautiful about this is that it captures the strangest part of cosmic expansion in one clean image. From the point of view of any dot, every other dot is moving away. No dot is special. No dot is the center. Every dot sees the same pattern. And that one detail matters more than people realize, because it breaks the most common misconception people carry about expansion: the explosion idea. In an explosion, there is always a center. There is always a place where it began. But on the surface of a balloon, there is no center on the surface itself. The expansion is not happening from one privileged point, it's happening everywhere. Every dot can honestly say, everything is moving away from me, and every dot would be right. That is why the balloon became the most popular way to teach the expanding universe. It explains why Hubble's law looks the way it does. It explains why we don't see a cosmic direction of expansion. It explains why, when we look at distant galaxies, we see them receding no matter which direction we turn. It even explains why the universe can look roughly the same in all directions without requiring a special location. But the balloon analogy also has a hidden poison inside it, a poison so subtle that you don't notice it until it has already rewired the way you imagine the cosmos. Because a balloon expands into something. It expands into the air around it. It expands into a room. It has an inside and an outside. And the human mind cannot stop noticing that fact. Even if you try to ignore it, your brain fills it in automatically. You begin picturing the universe as a balloon floating in a larger emptiness. And once that picture forms, the original question returns stronger than ever. If the universe is expanding, what is the room? What is it expanding into? This is the exact moment where the analogy, which was supposed to help, begins to mislead. Because the room in the balloon picture is not part of the lesson. It is not part of the universe. It is not required by cosmology. It is simply a trick we use to visualize a two-dimensional surface inside a three-dimensional space, because that's how human imagination works. We can't picture a curved surface unless we embed it inside something larger. But the universe does not need to be embedded in anything to expand. The balloon is meant to teach you about relationships between points on the surface, not about an external container. The surface is the universe in the analogy. The room is not. The problem is that our minds don't treat it that way. We don't just see the surface. We see the balloon as an object, and objects, in our experience, always exist inside something. So even when a physicist tells you, ignore the room, your brain refuses. It keeps asking where the balloon is located. It keeps trying to imagine the universe sitting somewhere. It keeps searching for a larger emptiness, a bigger space, a background reality. And this is why the question, into what, is so persistent. It's not because the universe is unclear, it's because our intuition is. The balloon analogy works brilliantly for one purpose. It shows how expansion can happen without a center, but it fails in another. It makes you believe that expansion requires an outside. The moment you truly remove the room from the analogy, the story becomes much stranger. Because once you stop imagining the universe as an object expanding into emptiness, you're forced to imagine something you've never experienced. Expansion as a change in distance itself. Not a thing moving through space, but the fabric of space stretching. Not galaxies flying outward like bullets, but the geometry between them evolving like a living grid. One upgraded way to picture it is like pixels on a screen. Imagine an old digital image made of dots. Each dot is a galaxy. Now imagine the screen itself changes. Not the dots moving across the screen, but the spacing between the dots increasing. The grid stretches. The distance between pixels grows. From the perspective of any one pixel, every other pixel appears to drift away. And yet, none of them are actually traveling through a background. There is no larger screen beyond the screen. The grid itself is the space. The expansion is the grid becoming larger. Another upgraded picture is even more unsettling because it doesn't rely on objects at all. Imagine you have a ruler. You put 2 coins on a table, one near you and one far away. Now imagine that overnight, without warning, the ruler itself changes. The inch marks spread apart. The ruler grows longer. You wake up and measure again, and suddenly the coins are farther apart. Not because either coin moved, but because the tool you use to define distance has stretched. The very meaning of 1 meter has changed. That sounds absurd in daily life. But cosmologically, it's close to what we mean by expansion. The universe is not a fixed stage where things move around. The stage itself can change its scale. The cosmic ruler can stretch. And once you see it that way, the universe stops feeling like a balloon in a room. It starts feeling like a world where the background is alive. This is why the expansion looks the same from every location. If you live inside a stretching grid, you don't see a special direction where expansion is coming from. You see every direction growing. You see every distant galaxy receding. You can point to one side of the sky and see redshift, then point to the opposite side and see the same thing. That symmetry is not a coincidence. It is a clue that the expansion is not a motion inside the universe, but a behavior of the universe itself. This is also why the question, "Where is the center?" dissolves. On a balloon surface, there is no center on the surface. In an expanding universe, there is no central location inside space. The only center you can talk about exists outside the analogy, in the higher dimensional room. But that room is not part of the universe. It is a visualization trick. It is the shadow of our imagination. And yet the balloon analogy remains powerful because it captures something deeply true. In an expanding universe, every observer can honestly say, "Everything is moving away from me," without making themselves special. That is a kind of cosmic democracy. No privileged viewpoint, no chosen location. Just a universe that expands evenly, like a law written into reality. But here's the twist. Even this upgraded picture can still mislead if we aren't careful, because it tempts us to treat expansion like a smooth mechanical stretching, as if space were made of rubber, as if it were a substance, as if it were a sheet you could grab and pull. Space is not rubber. Space is not fabric in the literal sense. The fabric of space-time is a metaphor, a useful one, but still a metaphor. What's actually changing is the geometry described by Einstein's equations. The distances between points in the universe change over time according to the energy and matter inside it. It's not a physical stretching in the way a balloon stretches, it's a change in the way the universe measures itself. That distinction matters, because it leads directly into the next mystery. If expansion is a property of geometry, not an object swelling outward, then expansion is not just something the universe does. It's something the universe is allowed to do, which means it must have a cause. And this is where the story becomes more than a visual puzzle, because the balloon analogy doesn't answer the deeper question. It only makes the expansion easier to picture. It does not tell you why expansion exists at all, why it began, why it continues, and why it follows the laws it does. The balloon makes the expansion look like a simple, natural behavior, like inflating a toy. But the universe is not being inflated by hands. There is no outside force blowing air into it. There is no cosmic pump. There is no room around it. So if there's no outside and no container and no external pressure, why is it expanding? That question is where cosmology stops being a picture and becomes a confrontation. Because once you remove the outside, you are forced to accept something that feels almost impossible. The expansion is coming from within the laws of reality itself, from the energy content of the universe, from the geometry of space-time, from something built into the structure of existence. And that is why the balloon analogy is both brilliant and dangerous. It gets you close enough to the truth that you can almost touch it. But it also plants the wrong image in your mind, an image that makes you keep asking about an outside. The balloon analogy helps you understand the pattern of expansion, but it also tempts you to believe the universe needs a room. The real universe does not. The real universe is the room. And now we're left with the question that the balloon can't answer, the question that forces the story to move forward. If expansion isn't motion, and it isn't an explosion, and it isn't swelling into emptiness, then what is driving it? So if there's no outside, why does expansion even happen? In 1915, long before anyone had proof that the universe was expanding, there was a man in Europe staring at a chalkboard like it was a battlefield. The room was quiet. The kind of quiet you only get late at night when the city outside has gone dim and the world feels far away. The air smelled faintly of dust and chalk. Equations covered the board in looping symbols, as if someone had tried to write the universe in a language only mathematics could speak. That man was Albert Einstein. And at the time, Einstein wasn't thinking about galaxies running away from each other. He wasn't thinking about redshift, balloons, or the Big Bang. He was thinking about something older and more basic: gravity. The same force that makes an apple fall. The same force that holds the moon in orbit. The same force that keeps the sun from tearing the solar system apart. For centuries, gravity had been treated like an invisible pull. Newton described it as a force that reaches across empty space instantly, like a mysterious thread connecting masses. It worked beautifully. It predicted the orbits of planets with stunning accuracy. It explained tides, the fall of objects, and the rhythm of the solar system. It became one of the most successful ideas in the history of science. But Newton's gravity came with a strange, almost magical assumption. Gravity acts across space without anything carrying it. One object influences another through nothingness. It was as if the universe allowed action at a distance, a silent tug through emptiness. Einstein couldn't accept that, not because it was wrong mathematically, but because it felt incomplete. It felt like a cheat. And he was living in a time when physics was changing in a way that made old assumptions dangerous. The speed of light had become sacred. Time itself was no longer absolute. Space and time were beginning to merge into something stranger. The universe was no longer a rigid stage. So Einstein asked a different question. What if gravity is not a force pulling through space? What if gravity is what space does? That single shift in perspective was a revolution. Because if gravity is not a force, then the universe isn't a stage where objects move under invisible pushes and pulls. The stage itself becomes active. The stage becomes flexible. The stage becomes something that can bend, stretch, and change. This became general relativity, Einstein's theory of gravity. And the easiest way to understand it is to stop imagining gravity as a hand reaching out to pull objects inward, and start imagining gravity as the shape of space-time guiding objects along paths. Mass tells space-time how to curve. Space-time tells mass how to move. That sentence became famous because it's the cleanest summary of a very deep idea. But the real shock is what it implies. Space and time are not fixed. They are not passive. They are part of the machinery of reality. And once you accept that, the expanding universe stops being a mystery of motion and becomes a mystery of geometry. Because the biggest misconception people have about expansion is the explosion picture. When people hear the universe is expanding, they imagine galaxies flying outward through space like fragments of a blast. On the largest scales, galaxies are not primarily flying outward through a background space. The distance between them increases because the space between them changes. The geometry of the universe evolves. And that difference sounds small until you realize it changes the entire meaning of reality. To make it clearer, imagine you're standing in an airport. You've just landed, and you're walking down a long corridor toward baggage claim. You step onto one of those moving walkways, a flat conveyor belt that carries you forward. Now imagine you stand still. You're not walking. Your legs aren't moving. And yet, you are still being carried forward. From your point of view, it feels like the ground itself is moving. You look ahead and see people drifting away from you. You look behind and see others falling back. Not because you're pushing through the air like a rocket, but because the walkway is moving beneath all of you. The motion is not entirely yours. It's built into the surface you're standing on. That is one of the closest everyday analogies we have for cosmic expansion. Galaxies can be relatively at rest in their local region, not using engines, not blasting outward, not traveling through a cosmic emptiness like bullets. And yet the distance between them grows because the underlying space-time is evolving. It's as if the cosmic walkway itself is moving. This is why the balloon analogy exists. It's why the pixel grid analogy works. It's why the ruler analogy feels unsettling. Because expansion isn't primarily about objects moving. It's about the definition of distance changing. And you might think this is just semantics. You might think, who cares whether galaxies are moving or space is stretching? Either way, they get farther apart. But it matters, because the universe behaves differently depending on which picture you choose. If galaxies were simply flying outward through a fixed space, there would be a center. There would be a location where the explosion happened. You could trace all the motion back to one point, like rewinding shrapnel. You could ask, where did it start? Where is the origin? Where is the middle? But the real universe doesn't give you that. The universe looks the same in every direction, from every location, on large scales. Every observer sees galaxies receding. Every region sees expansion. There is no privileged point you can label as the center of the cosmos. And that only makes sense if expansion is not an explosion inside space. It makes sense if expansion is space itself. It is the geometry. It is the metric, the mathematical description of how distances work in the universe, changing with time. That is why Einstein matters in this story. Hubble gave us the observation. Galaxies are receding, but Einstein gave us the framework that allowed us to understand what that observation really meant. Einstein's equations didn't just describe how planets orbit. They described how the universe itself could evolve. They allowed for expanding solutions. They allowed for contracting solutions. They allowed for universes that change shape over time. And in one of the most ironic twists in scientific history, Einstein himself initially resisted that implication. He believed the universe should be static, eternal, unchanging, balanced. When his equations suggested the universe might expand or contract, he considered it unacceptable. So he added an extra term to his equations, a mathematical patch designed to hold the universe still. He called it the cosmological constant. It was a kind of stabilizer, a way to force the universe to remain static because the idea of a changing universe felt too radical. Then Hubble's data arrived, and the universe refused to stay still. Einstein reportedly called his cosmological constant his biggest blunder. And for decades, that story became a famous cautionary tale in science, a reminder that even geniuses can cling to the comfort of an old worldview. But the deeper lesson was this: the universe is not obligated to match our intuition. Space-time is not obligated to be still. Once you accept general relativity, the expanding universe stops being weird in one way and becomes weird in another, because you no longer have to imagine galaxies flying outward into emptiness. You can imagine a universe where space-time itself changes. A universe where the distance between 2 points is not fixed. A universe where the cosmic grid stretches. A universe where reality is not a rigid container, but an evolving geometry. And suddenly, the original question, into what, begins to dissolve, because expansion isn't a thing traveling into an outside. It's a behavior of the inside. It's an evolution of the universe's own shape. But here is where the story becomes darker, because in a universe governed by general relativity, expansion is not just a curiosity, it's a physical process, controlled by energy and matter. It can slow down, it can speed up, it can change over time. And for most of the 20th century, scientists assumed expansion should be slowing down. That assumption felt almost inevitable. If you throw a ball upward, gravity slows it down. If the universe began with a hot, dense beginning and everything has been separating ever since, then gravity should be acting like a cosmic brake. The mass of the universe should be pulling everything back, slowing the expansion. It might not stop it completely, but it should at least be decelerating. That's what almost everyone expected, and it was a reasonable expectation. Because gravity in general relativity is not just local. The mass and energy of the universe shape the overall geometry. They influence how expansion behaves. If there is enough matter, the universe could even stop expanding and collapse back inward. A big crunch. A reverse of the Big Bang. A universe that lives, expands, and then dies by falling back into itself. For decades, cosmology was haunted by that possibility, not because it was poetic, but because it was plausible. The fate of everything seemed to depend on a single question. Does the universe contain enough matter to slow itself down? Then, near the end of the 20th century, scientists measured the expansion more carefully. Not just the fact that galaxies are receding, but the rate at which that recession changes over time. They tried to see if the cosmic walkway was slowing, if the stretching of space-time was easing, if gravity was winning. And what they found was not just surprising, it was terrifying. Because the expansion wasn't slowing down, it was speeding up. And once you discover that, the story of the universe changes again. From a universe that expands because of an initial push, to a universe that expands because something is driving it from within. Something hiding inside the vacuum. Something built into space itself. In 1998, the universe was supposed to be doing something simple. It was supposed to be slowing down, not because anyone had a philosophical preference for a slow universe, but because the logic seemed unavoidable. If the universe began hot and dense, if it began expanding outward from an early compressed state, then gravity should be acting like a cosmic brake. Every galaxy, every cluster, every strand of matter should be tugging on everything else. Even if the universe kept expanding forever, it should at least be decelerating, losing momentum over time, the way a thrown object loses speed as gravity pulls it back. For most of the 20th century, this wasn't really debated. It was assumed. It was the default story. The universe expands, gravity slows it, and the future depends on how much matter exists. If there's enough matter, the expansion stops and reverses. If there isn't, it expands forever, becoming colder and emptier with time. It felt like a clean, cosmic drama. And then at the end of the century, a group of scientists decided to actually measure it. Not guess, not assume, measure. To do that, they needed a way to look far back in time, not just to distant galaxies, but to events so bright they could be seen across billions of light years. They needed a kind of cosmic lighthouse, something that would shine with a predictable brightness so that distance could be calculated. And the universe, strangely, provided one. Supernovae. But not just any supernovae. A specific type called Type 1a supernovae. Explosions so luminous that for a brief moment they can outshine an entire galaxy. These events happen when a white dwarf star, the dead core of a sun-like star, steals matter from a companion until it reaches a critical mass. Then, in a runaway nuclear reaction, it detonates. What makes Type 1 a supernovae so valuable is that they are, in a cosmic sense, consistent. Not identical, but consistent enough that astronomers can treat them as standard candles. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it must be. It's the same logic as seeing a street lamp at night. If you know how powerful the bulb is, the dimness tells you the distance. So in the late 1990s, two major teams of astronomers, working independently, began hunting for these explosions in distant galaxies. They weren't just collecting pretty images, they were trying to measure the expansion history of the universe. They wanted to see how the expansion rate changed over time. They wanted to confirm what everyone expected, that the universe was slowing down. Picture the scene. Not grand domes on mountaintops this time, but modern observatories and cramped offices, computer screens glowing in dark rooms, coffee cups, late nights. The kind of work where you stare at numbers until they stop looking like numbers and start looking like a threat. Because these teams weren't dealing with a few galaxies. They were dealing with the universe at enormous distances, billions of light years away. Meaning, they were seeing the universe as it was, billions of years in the past. Every supernova was not just a measurement of distance, but a message from an earlier era of cosmic history, and the method was conceptually simple. First, find a Type 1a supernova in a distant galaxy. Second, measure how bright it appears. Third, compare it to how bright it should be. That gives you distance. Then measure the redshift of the host galaxy. That gives you how much the universe has expanded since that light was emitted. Distance plus redshift is the key combination. It tells you not only that the universe is expanding, but how the expansion rate has evolved. And at first, everything looked normal. The numbers lined up. The results felt like they were falling into place. But then the teams began to push farther out, to older supernovae, deeper in time, and the data began to shift in a way that didn't fit the expected story. The supernovae were too dim, not slightly dim, systematically dim, as if they were farther away than they should be. At first, you might think this is just an error. Dust could be blocking light. The supernovae could be different in the distant past. The calibration could be wrong. The telescopes could be missing something. And the teams did what scientists always do when reality misbehaves. They doubted themselves first. They checked everything. They argued. They reran calculations. They questioned assumptions. Because what the data was hinting at was not just surprising, it was almost unacceptable. The universe was not slowing down, it was speeding up. That sentence should feel wrong, because it is wrong according to everyday experience. If you throw a ball into the air, it slows. It doesn't accelerate upward. Gravity pulls it back. That's how the world works. And the universe filled with matter and gravity should behave the same way. Expansion should be losing speed, not gaining it. But the supernovae were telling a different story. They were telling us that the universe's expansion was accelerating, that sometime in the last several billion years, something changed. The cosmic break did not win. The universe did not gradually coast toward a slower expansion. Instead, the expansion began to pick up speed, as if some invisible engine had turned on. And this is the moment where cosmology becomes unsettling in a new way. Because an expanding universe is strange, but an accelerating expanding universe is terrifying. It means the future is not just emptier, it's emptier faster. It means the universe is not simply coasting, it is being pushed. And the push is coming from somewhere. The problem was, nobody knew where. Because in Einstein's universe, gravity doesn't just pull. Under certain conditions, it can also behave as if it repels. Not by reversing direction like a magnet, but by changing the way space-time evolves. General relativity allows for a universe where certain kinds of energy cause space itself to expand faster and faster. And suddenly, a forgotten term in Einstein's equations returned like a ghost. The cosmological constant. The thing Einstein had once invented to keep the universe still. The thing he had once called his biggest blunder. Now it looked less like a blunder and more like a prophecy. Because the simplest explanation for acceleration was that empty space itself contains energy. A kind of vacuum energy. A background pressure built into the fabric of the cosmos. Not energy in the form of stars or gas or matter, but energy of space itself. And when space expands, there is more space, so there is more of that energy. And if that energy pushes expansion, then the universe can accelerate. This is where the phrase dark energy was born. Not because it was a neat name, but because it was an admission. Dark energy means we see its effect, but we do not know what it is. We can measure it. We can describe it mathematically. We can estimate how much of it exists, but we cannot point to it in a lab. We cannot bottle it. We cannot photograph it. It is a name for a force we can feel in the equations, but cannot touch. And what made it even more unsettling was the scale. The matter and stars and galaxies, everything we normally think of as the universe, turned out to be a minority, a small fraction. The acceleration implied that most of the universe is something else, something invisible, something that does not clump into galaxies, something smooth, spread out, and deeply strange. The universe, it seemed, was not dominated by the things we can see. It was dominated by something hiding in the vacuum. And the supernova teams didn't discover this in a dramatic single moment. It wasn't like a movie where someone slams their fist on the table and shouts, "It's accelerating." It was worse than that. It was slow. It was incremental. It was the creeping realization that the data would not go away. That no matter how many times you checked, the dimness remained. That the universe was telling you something you didn't want to hear. The expansion is speeding up. And once you accept that, the story becomes darker. Because acceleration changes the meaning of expansion. It's no longer just the universe getting bigger. It's the universe becoming dominated by the growth of space itself. Because if empty space has energy and the universe expands, then the amount of empty space increases. And if the amount of empty space increases, then the amount of that energy increases. And if that energy drives expansion, then expansion feeds itself. It becomes self-reinforcing, a runaway effect. And at this point, the original question returns one more time, but in a new form. Because it's no longer just into what is the universe expanding. Now it becomes, if space itself is stretching faster, Does that mean the universe is creating new space? Not just increasing distances, but generating more room inside reality itself? Because if the expansion accelerates, it begins to feel less like a passive stretching and more like something active, like the universe is manufacturing its own geometry as it goes. And once you start thinking that way, you begin to wonder something even stranger. If the universe can create more space inside itself, what does that even mean for the concept of nothing? What does it mean for the vacuum? And if dark energy is real, is it constant? Or could it change? Because if it changes, the fate of the universe changes with it. And the truth is, we don't yet know which story we're living in. We only know this: the universe is not slowing down. It is accelerating. And that single fact forces us to confront a final, haunting possibility. Maybe the expansion isn't just something that happened after the beginning. Maybe the expansion is the universe's deepest behavior. Maybe space itself is not a passive stage. Maybe it is the main character. And if that's true, then the question, into what, was never the right question. The real question is, what is space if it can push the universe apart? And what happens if that push never stops? By this point in the story, we've walked right up to the question that started everything. The one that refuses to leave your mind, no matter how many analogies you hear, no matter how many scientists you meet along the way. If the universe is expanding, what is it expanding into? And now, after everything we've uncovered, we can finally answer it directly. Not with poetry, not with a metaphor, with the cleanest truth modern cosmology can give. The universe is not expanding into anything. Space is not growing inside a larger container. Space is the thing that is changing. That is the core idea. And it sounds almost too simple until you realize it forces you to abandon one of the deepest habits your brain has: the habit of imagining a background. Because in everyday life, space feels like emptiness. It feels like the absence of things, the nothing that sits between objects, the silent room around matter, the gap between stars, the blackness between galaxies. But in modern physics, space is not just the absence of matter. Space has structure, space has rules, space has behavior, and most importantly, space has geometry. In general relativity, space and time form a single thing: space-time. And the way space-time is shaped is not just an artistic description, it is a mathematical object, a geometry, a metric, a set of relationships that define what distance means, what time means, and how the universe measures itself. When cosmologists say the universe is expanding, what they really mean is that the metric is changing. The scale of space-time is evolving. The universe is not a cloud of matter rushing outward into emptiness. It is a geometry whose distances grow over time, and that is why the question, into what, is so difficult, because it assumes there is a fixed space out there that the universe is moving into. It assumes a background, a larger stage, a cosmic room. But in the modern picture, the universe is the stage. There is no larger space behind it. There is no outside that space is flowing into. The expansion is internal. It's the universe stretching itself. And once you accept that, the question changes. It becomes, is new space being created? Because if the metric changes, if distances grow, if the universe gets bigger without moving into anything, then something must be happening to the very fabric of reality. Something must be generating more room inside the universe itself. And the answer is yes. In a very real sense, new space is being created. But not the way we normally imagine creation. not like a factory producing material, not like an engine pumping out extra space. More like a rule of geometry allowing the distances between points to increase. To understand this, imagine the universe as a network of points, galaxies, clusters, structures. Now imagine that the relationships between those points change. The distance between every pair increases. Nothing has to move through a background for that to happen. The background is the distance. The background is the rule. The universe becomes larger because the definition of far changes. And this is the part that feels almost like cheating, because it sounds like we're using words to escape the question, but we aren't. This is genuinely how the physics works. In cosmology, the expansion is not a motion through space. It is the stretching of space itself. And once you say that out loud, the next thought arrives almost immediately. If space itself can stretch, then empty space is not truly empty. Because if it were truly nothing, it couldn't have behavior, it couldn't stretch, it couldn't push, it couldn't accelerate the universe. A true nothing cannot do anything. And yet, the universe is accelerating, which means the vacuum, the emptiness between galaxies, must have properties. This is one of the most unsettling discoveries of modern physics. The vacuum is not nothing. The vacuum is not just blankness. The vacuum is a physical thing. Even in the emptiest region of space, far from stars and dust and gas, quantum physics tells us that the vacuum is still alive with fields. Quantum fields exist everywhere. They don't vanish when matter is absent. They remain, quietly vibrating. And even when those vibrations average out, even when there are no particles, the vacuum can still contain energy. Vacuum energy. A background pressure, a hidden property of space itself. And once you accept that, the idea of expansion becomes even stranger. Because now the universe isn't just stretching a passive emptiness. It's stretching something that has a measurable effect, something that can influence gravity, something that can push. This is why dark energy is so terrifying. Because dark energy is not located in stars, it's not stored in galaxies, it doesn't sit in clusters like a gas cloud. Dark energy appears to be a property of space itself, which means that as the universe expands, there is more space. And if dark energy is tied to space, then there is more dark energy. And if there is more dark energy, then the expansion can accelerate. And if the expansion accelerates, then the universe creates more space even faster. The universe becomes a feedback loop, not of matter, but of geometry. At this point, it becomes natural to ask, is space being created in the way matter is created? Is something being added to the universe? The answer is subtle. Space is not a substance. It is not a material. It's not made of atoms. But the metric, the structure that defines distances can evolve. So, creation of space is not the creation of a thing. It is the growth of a relationship. And the closest analogy we have in everyday life is digital. Imagine a low-resolution image on a screen, a simple grid of pixels. Each pixel is a point. Now imagine you increase the resolution. You don't move the original pixels around like physical objects. Instead, the grid becomes finer. More pixels appear between the original ones. The image becomes larger in informational detail. There is more room inside the same frame. Now, that analogy isn't perfect, but it captures something important. You can increase the space between points without needing an external container. You can create more structure inside the system itself. More spacing, more resolution, more geometry. Cosmic expansion is not exactly that, but it's close in spirit. The universe doesn't expand into a room. The room is the universe. the distances inside it increase. More space appears between galaxies, not because galaxies are being pushed into an outside, but because the scale of the universe changes. And this is the point where we can finally answer the question in the simplest possible way. The universe is expanding into nothing, not because there is an empty void outside it, but because outside may not exist. Expansion is the universe changing its own metric. The distances between points grow because the geometry evolves. Space is not moving outward. Space is what's changing. And yet, even after all that clarity, the human mind still rebels. Because part of you still wants to imagine an outside. Part of you still wants to ask, where is it happening? Where is the universe located? What is the universe sitting in? And that instinct is not childish. It's deeply human. Because every system we know exists inside something larger. A house exists in a city. A city exists on Earth. Earth exists in the solar system. The solar system exists in the Milky Way. The Milky Way exists in a larger cosmic web. So our minds naturally assume the universe itself must be one more layer in that nesting pattern, a thing inside a bigger thing. But the universe is the one place where that nesting might end. The universe might be the final container. And if that is true, then asking what it expands into is like asking what is north of the North Pole. The words are correct, but the concept breaks. Still, there is one last twist we can't ignore, because even if the universe does not require an outside to expand, physics does not strictly forbid the idea that something could exist beyond what we can observe, not beyond the edge of space, because there may be no edge, but beyond the limits of our access, beyond the horizon. Because the universe is not just expanding, it's expanding in such a way that there are regions we will never see. The expansion is fast enough that light from certain distant places will never reach us, no matter how long we wait. Those regions are not outside the universe, but they are outside our causal reach. They are cut off from us by the growth of space itself. So even if the universe has no outside in the classical sense, it still has boundaries in a different sense. Boundaries of communication, boundaries of observation, boundaries of cause and effect. And that is where the story becomes haunting again. Because if the universe contains regions we can never see, never interact with, never reach, then there could be structures beyond our horizon that we will never know about. There could be other parts of the universe that are effectively separate from us, not because they're in another dimension, but because expansion has pulled them beyond the limit of contact. And once you accept that, a forbidden question returns in a new form, not what is outside the universe, but what if there is an outside and we can't access it? What if the universe we see is only one region of something larger? What if our cosmic horizon is not the edge of reality, but the edge of what we can ever measure? Because if that's true, then the universe might not expand into anything, but it might still be part of something bigger, something hidden, something unreachable. And the moment you step into that possibility, you find yourself standing at the doorway of one of the most controversial ideas in modern cosmology: inflation, bubble universes, and the haunting possibility that our universe is not the whole story, just one bubble in a much larger cosmic sea. To understand why some scientists even dare to talk about an outside, we have to return to the beginning. Not the poetic beginning, not the religious beginning, the physical beginning. The earliest moment our equations can still speak about without breaking into nonsense. A fraction of a second after the Big Bang, not minutes, not hours, not even a heartbeat, A sliver of time so small that the human mind can't feel it. A time before atoms, before stars, before light could travel freely, before the universe was transparent, before anything we would recognize as a world existed at all. And in that earliest moment, the universe may have done something that makes the expansion we see today look gentle. It may have inflated. Inflation is one of the strangest and most powerful ideas in cosmology, and what makes it so difficult to accept is that it sounds like a patch, like something invented to fix problems in the Big Bang model. But inflation isn't just a patch, it's a door. Because if inflation is real, then the question, expanding into what, changes again. It becomes more dangerous, more cinematic, and possibly more true than we're comfortable admitting. The simplest way to describe inflation is this. In the earliest moment of the universe, space expanded at an unimaginable speed. Not just fast, but exponentially fast, doubling and doubling again in an explosion of geometry so violent that the universe could go from subatomic size to something larger than a galaxy in a blink of cosmic time. And what's crucial is that inflation wasn't matter rushing outward, it was space itself. The metric changing, the fabric of the universe swelling like a storm. Why would it do that? Because according to the theory, the early universe was dominated by a special kind of energy, a field with properties unlike normal matter and radiation. This field acted like a repulsive form of gravity. It didn't pull space inward, it pushed space outward. It caused space-time to expand faster and faster, like a runaway effect. Then, in most versions of the theory, inflation ended. The field decayed, its energy converted into particles and radiation. And the universe became the hot, dense fireball we call the Big Bang. In other words, inflation isn't separate from the Big Bang. Inflation is the prelude, the moment before the universe became the universe we recognize. And inflation was invented because the Big Bang model had puzzles, deep puzzles that looked like cracks in the story. One of them was the horizon problem. Why does the universe look so smooth and uniform in all directions, even though distant regions shouldn't have had time to communicate? Another was the flatness problem. Why is the geometry of the universe so close to perfectly flat, like a stretched sheet? Inflation answered these problems in a single move. If the universe expanded violently in its earliest instant, it would smooth itself out, like wrinkles pulled tight. It would take a tiny, connected patch and stretch it until it became the vast cosmos we see today. It was elegant. It was powerful. And for many scientists, it felt like the missing piece. But then the theory did something unexpected. It grew. Because once you introduce inflation, you open a terrifying possibility. What if inflation didn't end everywhere? What if it ended in our region but continued in others? What if the early universe wasn't a single event but a process? This is where the phrase eternal inflation enters, and where cosmology begins to sound like science fiction, even though it comes from serious mathematics. Eternal inflation proposes that inflation is not a one-time explosion that happens and stops. Instead, it's something that can keep happening in the background. In some regions, inflation ends and forms a universe like ours. In other regions, inflation continues, expanding space faster than it can decay. And if that's true, then the cosmos becomes a kind of endless inflating ocean. A background of space expanding exponentially forever. Inside that inflating background, bubbles form. Each bubble is a region where inflation ends, where energy converts into matter and radiation, where a Big Bang happens locally, where a universe begins. Our universe would be one bubble, not the bubble. One. And the moment you say that, the question, expanding into what, becomes almost unrecognizable. Because now you can answer it with a cinematic maybe. Maybe the universe is expanding into nothing, but maybe our universe is expanding inside a larger, inflating background. Not a room in the everyday sense, not a simple empty container, but a deeper structure of space-time that continues beyond our observable horizon. A multiverse. And the most haunting part is that, in this picture, there may be infinitely many bubbles. Infinitely many universes. Each one a separate region of space-time, with its own history, its own galaxies, its own cosmic microwave background, its own Big Bang moment. And perhaps, in some versions, its own laws of physics. Because if inflation is driven by a field, and that field can settle into different states, then different bubbles might freeze into different physical realities, different values for constants, different particle families, different strengths of forces, different outcomes, a landscape of universes. Reality not as a single law, but as a family of possibilities. This is where the idea becomes dizzying, because it makes the universe feel less like a singular thing and more like a biological process. A cosmic ecosystem generating countless regions, each one self-contained. And the best everyday analogy for this is not a balloon, it's boiling water. Imagine a pot on a stove. The water begins to heat. At first it looks calm, then tiny bubbles form at the bottom. They grow, they detach, they rise. More bubbles form. The process continues as long as heat is supplied. In eternal inflation, the inflating background is like the boiling water, a state that continues. And bubble universes are like the bubbles. Pockets where a phase change occurs, where inflation ends locally, where a universe is born. Each bubble is separate. Each bubble expands from the inside. Each bubble contains its own space. And from within a bubble, the inhabitants might never see the inflating background. They might never detect the other bubbles. The walls between bubbles could be unreachable. The expansion could isolate each bubble forever, turning each universe into its own sealed reality. If that is true, then the word outside becomes strange again, because there would be an outside in a mathematical sense, an inflating background beyond our bubble. But it would not be a place we can travel to. It would not be a region of space we can point to with a telescope. It would be a deeper layer of the cosmic structure. And this is why the multiverse is such a seductive idea. It gives you a way to imagine an outside without returning to the childish picture of a balloon in a room. It replaces the room with a process. It replaces the container with a deeper geometry. It turns the universe into one region of a larger inflating reality. But the moment you step through this door, the story becomes more dangerous, because now the question isn't just, what is the universe expanding into? Now it becomes, how big is the whole thing? And does the whole thing even have a boundary? Because in eternal inflation, the inflating background expands faster than bubbles can fill it. That means the process never completes. The multiverse becomes an endless generator, a cosmic machine that keeps producing universes endlessly without a final stopping point. It's not just bigger than we can observe. It may be bigger than any number we can write. And at this point, you might feel the old skepticism rising. The same skepticism that kept scientists cautious for decades. Because yes, this is cinematic. Yes, it's elegant. Yes, it's one of the most mind-stretching ideas humans have ever produced. But is it real? Or is it just a beautiful story we tell ourselves because we can't stand the idea of a universe without an outside? This is where the multiverse becomes controversial. Because inflation itself has some observational support. It predicts patterns in the cosmic microwave background. It explains why the universe is smooth. It explains why it's flat. It solves problems that otherwise feel like miracles. But eternal inflation, the multiverse version, is harder. Much harder. Because if other bubbles exist beyond our horizon, then by definition we cannot see them. We cannot receive light from them. We cannot send signals. We cannot travel there. The expansion isolates us. The boundary becomes unreachable. So, how do you test it? How do you do science on something you can't observe? Some physicists argue that there may be subtle signs, faint imprints in the cosmic microwave background from a collision between bubbles, for example. A bruise in the baby picture of the universe. A strange asymmetry. A pattern that shouldn't exist. But so far, nothing conclusive has been found. Others argue that the multiverse is not science at all. Not because it's false, but because it may be untestable in principle. And if something is untestable in principle, then it sits in a strange place. It's a mathematical possibility, a philosophical implication, but not an experimentally grounded fact. And that is why the multiverse door is so unsettling, because it offers the most satisfying maybe answer to the question of outside. But it also forces you to confront the boundary between science and storytelling. It makes you ask whether the universe is a single reality or a vast cosmic foam. It makes you wonder whether our laws of physics are fundamental or local. It makes you wonder whether the universe is expanding into nothing or expanding inside a larger inflating background that we will never touch. And it brings us to a final cliffhanger, the kind that doesn't just pull you into the next chapter. It forces you to question what counts as knowledge at all. Because the multiverse might be real. It might be the deepest structure of reality. It might be the true answer hiding behind the question, into what? But it might also be the most beautiful story physics has ever produced. A story born from equations, not observations. So the question becomes unavoidable. But is that real science? Or just beautiful storytelling? After inflation, after bubble universes, after the multiverse door swings open and the imagination runs wild, there's a moment every honest cosmologist eventually has to face. A moment where the story stops being cinematic and becomes scientific again. Because the universe doesn't care what feels satisfying. It doesn't care what sounds beautiful. It doesn't care what makes a perfect ending to a documentary. Science has a stricter rule. You don't get to keep an idea just because it's elegant. You only get to keep it if the universe agrees. And the only way to know whether the universe agrees is through something far less romantic than theory. Measurement. This is the point where we have to step back and ask what we actually know and what we are only guessing. Because when people hear words like multiverse, it's easy to imagine cosmology as a kind of modern mythology. Brilliant scientists replacing ancient gods with equations, telling stories about realities we can never see. And in some cases, that criticism is fair. Not because cosmologists are dishonest, but because the universe is brutally hard to test. The biggest questions we ask are often the hardest questions to answer. Not because we lack intelligence, but because we lack access. We live inside the universe. We don't get to step outside it. We don't get to look at it from the outside like a globe on a table. We are trapped inside the system we're trying to understand. And that makes cosmology different from almost every other science. You can test chemistry in a lab. You can repeat an experiment in biology. You can build machines to probe particles. But you can't run a second universe to compare results. You can't restart the Big Bang. You can't adjust constants and see what happens. You get one universe, one set of observations, and you have to reconstruct everything from the inside. So, what can we actually measure? The first thing we can measure is redshift, the stretching of light. When we look at distant galaxies and see their light shifted toward the red, we know the wavelengths have been stretched, and that stretching correlates with distance. The farther away the galaxy, the more its light has been stretched by the expansion of space. That is not philosophy, that is data. It is repeatable, measurable, and one of the strongest pieces of evidence we have that the universe is expanding. The second thing we can measure is large-scale structure, the cosmic web. The universe is not random. Galaxies are not scattered like dust in a room. They form filaments, clusters, walls, and enormous voids. Patterns that stretch across hundreds of millions of light years. And those patterns match what you would expect in a universe that began with tiny fluctuations and then grew under gravity while space expanded around them. This isn't a vague aesthetic. It's a statistical fingerprint, something we can simulate, compare, and test. And then there is the most haunting measurement of all, the cosmic microwave background. The CMB is the universe's baby picture, a faint glow filling all of space, arriving from every direction, left over from a time when the universe was only about 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. Photons were trapped, constantly scattered like headlights in thick fog. But as the universe expanded, it cooled. And at a certain moment, atoms could form. The fog cleared, and light was finally released. That light has been traveling ever since. And because the universe has expanded, that ancient light has been stretched into microwaves. A whisper of heat so faint it almost feels impossible that we can detect it at all. But we can. And the CMB is not just proof the universe had a hot beginning. It is a map of the universe's earliest structure. Tiny temperature variations, 1 part in 100,000, show where matter was slightly denser and where it was slightly emptier. Those tiny fluctuations are the seeds of everything. The seeds of galaxies, clusters, and the cosmic web itself. The universe we see today grew from those faint ripples. This is the part of cosmology that is deeply grounded. It is observational, it is measurable, it is evidence. But then we hit the wall. Because there are things we cannot measure. Not yet, and maybe not ever. We cannot measure an outside. We cannot directly observe a multiverse. We cannot look beyond our cosmic horizon. We cannot test what exists in regions of space-time that are causally disconnected from us. And that's not a limitation of technology, it's a limitation of physics. The universe expands, and because of that expansion, there are places whose light will never reach us. They are not outside the universe, but they are outside our reach. And that means there may be parts of reality that are forever hidden, not because they are protected, but because the geometry of space-time makes them unreachable. This is where the idea of outside becomes strange, because when people ask what the universe is expanding into, they imagine an edge. They imagine a boundary where the universe ends and something else begins. But the universe may not have an edge in that sense. It may be finite without a boundary, like the surface of a sphere. Or it may be infinite. Or it may be something even stranger, curved in a way we can't fully picture. In any of those cases, outside might not be a meaningful concept. Not because we are ignorant, but because the universe may not be the kind of thing that has an outside. The question may be like asking what is north of the North Pole. The words fit together, but the idea breaks because it assumes a geometry that doesn't apply. And this is why critics exist in cosmology. Not critics who deny the expansion, that part is solid, but critics who challenge the more cinematic leaps. Critics who say, inflation is plausible, but eternal inflation may be untestable. The multiverse might be mathematically allowed, but if it cannot be observed even in principle, does it belong in science? Or does it belong in philosophy? Some physicists argue that a theory can still be scientific if it makes indirect predictions. If eternal inflation predicts certain patterns in the CMB, or if it explains why the universe has the constants it has, then maybe it has scientific value. Others argue that this is dangerous, that it blurs the line between physics and storytelling, that it risks turning cosmology into a field where elegance becomes evidence. And here, in the middle of this debate, we arrive at something even more unsettling. Because no matter what you believe about inflation or the multiverse, one fact remains. The expansion is accelerating. That is not a poetic idea. That is a measured result. And it means that the future of the universe is not just about what it expands into. It's about what expansion does to everything inside it. Because expansion is not just a background detail. Expansion is destiny. If dark energy stays constant, if it behaves like a true cosmological constant, then the universe will continue expanding forever. Galaxies will drift farther apart. Clusters will become isolated islands. Over trillions of years, stars will burn out. New star formation will slow. The sky will grow emptier. The universe will become bigger, colder, and quieter. Not in a dramatic apocalypse, but in a slow fading, a cosmic loneliness. This is often called heat death, but the name can be misleading. It doesn't mean the universe ends in fire. It means the universe ends in stillness, in maximum entropy, in a state where there is no more usable energy, no more gradients, no more meaningful change. A universe that continues to exist, but no longer does anything interesting. And if you imagine life in that far future, it becomes haunting. The night sky would no longer be filled with galaxies. The cosmic web would be gone from view. Most of the universe would be invisible. Any civilization that evolves late enough might look into space and see almost nothing and conclude, wrongly, that the universe is empty, that the cosmos is small, that their galaxy is the whole thing. They would be trapped in an illusion created by expansion itself. But there is a darker possibility. What if dark energy increases? What if it grows stronger with time? If dark energy becomes more intense as the universe expands, then the acceleration doesn't just continue, it intensifies. The stretching becomes violent. The expansion begins to overcome not just galaxies and clusters, but gravity itself. First, clusters fall apart, then galaxies unravel, then star systems lose their orbits, then planets drift. Then even atoms and molecules are torn apart as space stretches faster than the forces holding matter together. This scenario is called the Big Rip. And it is one of the most terrifying fates physics allows, because it is not just the death of stars, it is the death of structure, the death of stability. The universe doesn't fade, it shreds. But there is another possibility, and in some ways it is even more unsettling than either heat death or the Big Rip. What if dark energy changes? What if it isn't constant? What if it evolves in a way we don't yet understand? Then the fate of the universe is unknown. The acceleration could slow, it could stop, it could reverse. The universe could approach a new state. The laws could behave differently in the far future. Expansion could be a phase, not an eternal rule. And right now, we don't know which story we're living in. We can measure dark energy's effects today, but we cannot yet fully explain its nature. We don't know whether it is truly a constant property of space or whether it is a field that changes. We don't know if it is a sign of new physics or a misunderstanding of gravity itself. We don't know if it will remain steady for trillions of years or shift in ways that rewrite the future. And this is where the emotional weight of the story lands. Because the expansion of the universe is not just a fact about galaxies, it is a fact about meaning. It tells us something uncomfortable. The universe is not designed to stay familiar. The cosmos is not built to preserve the conditions that allow complexity. It expands, it cools, it changes. And in the long run, it may erase the very evidence that allowed us to discover it. The universe is getting bigger, but it is also getting quieter. And when you zoom out far enough, the expansion begins to feel like more than a physical process. It begins to feel like a slow transformation of reality itself. A transformation where the universe becomes more empty, more isolated, more distant from its own past. Expansion may not just change space, it may change meaning. And now comes the final question, the one nobody likes. The question we started with still sounds simple. If the universe is expanding into what? It's the kind of question that feels like common sense, because everything in our lives expands into something. A fire spreads into a forest. Smoke fills a room. A balloon inflates into the air around it. Even a growing city pushes outward into open land. There is always an outside. There is always more space waiting. So when you hear that the universe is expanding, your mind does what it has always done. It reaches for the same picture. It imagines the universe as an object inside a larger emptiness, a bubble swelling outward into a cosmic room. But after everything we've seen, the quiet truth is almost the opposite of that picture. The universe is not expanding into anything, not because we haven't found the outside yet, but because there may be no outside to find. In modern cosmology, expansion is not a thing moving outward through a bigger space. It's not galaxies flying away like shrapnel from an explosion. It's not the universe swelling into a surrounding void. Expansion is the universe changing its own geometry. The distances between galaxies grow because the metric grows. The cosmic ruler stretches. The definition of far evolves. Space isn't a container the universe sits inside. Space is part of the universe. So when the universe expands, what changes is not where the universe is located. It's what distance means inside it. And once you accept that, the original question becomes something stranger than a puzzle. It becomes a mirror. Because what you're really confronting isn't just the universe. You're confronting the limits of human intuition, the part of the mind that refuses to accept a reality without a background, without an outside, without a final wall where the unknown can stop. But the universe may not be built that way. It may be finite, without an edge, like the surface of a sphere. Or it may be infinite, with no boundary at all. Or it may be part of something larger that we can never reach because expansion has placed it beyond our horizon forever. In every case, the same unsettling idea returns. We are inside a reality where outside might not exist. And maybe that's the strangest part of all. Not that the universe is expanding, not that it's accelerating, not that empty space has energy, but that the universe doesn't need a place to expand into, because it is the place.